we can use the material properties into design data, into design tables. Finally, when you do a structural design, you want to know the elastic modulus, you want to know the Poisson's ratio, you want to know the flexural strength, you want to know the stiffness, right? You want all those parameters. So we did compressive stress-strain relationships, and I think I have here. So here is stress versus axial strain and stress versus radial strain. So triaxial test basically, not triaxial, uniaxial test, just with triaxial measurements. So you push it, your axial strain in this direction, your lateral strain or radial strain in this direction. So here is, again, the scales are different and all of that, so look carefully here. This is the plain mixes without fiber. You can get to 20 KSI. It's in the US it's all PSI and KSI. So KSI is kips per square inch. 1 kip is 100 pounds. So this is 25,000 pounds per square inch. 150 pounds per square inch is 1 megapascal. So 25,000 pounds per square inch is about 160 megapascal. 160 megapascal. Okay. Or no, 25 is 25 times 15. 25 divided by 15. 25 divided by 15. So 101, about 175 megapascal. So you get about 150, 160 megapascal strength, but you see that you have an axial strain of about 0.4%. Remember, when you do your reinforced concrete design, what is the maximum usable compressive strain in concrete? 0.0035. In Europe, India, and Canada is 0.0035. In the US it's 0.003. Okay, so we use only 0.3% or 0.35%. So you can see here, even if you want to use the maximum usable compressive strain, you still are okay, right? For design. But because of the very high strength, you would not want to get to 0.3. You would want to stop at a much lower strain. You probably would want to 0.25 or so, and that's fairly good for that. And then look at the axial radial strain. You have a much higher, and again all these tests were done under radial strain control, so you can get very high, very nice strain descriptions. You get a maximum radial strain at about 60-70% stress of about 0.3%. Very good radial strains. Now if I put in 1% fibers, the story completely changes. Look at how now the axis here instead of 0.5 gets up to 1. Do you see the post-peak behavior in compression and the post-peak radial behavior in compression? So with fibers, you get extremely high ductility. Look at 1% radial strain, 1.2% radial strain, which means you're letting your Poisson effect take effect so much without breaking the specimen. It's the fibers are holding them so that you can take much higher load. So effective fiber content, you can see here cracking strength with 1% and 3% fiber volume up to 3000 psi, that's about 20 megapascal. So cracking strength or flexural strength of 20 megapascal. Okay, so M20 in flexural strength, not compression. Typically your flexure is what? 1/10 of your compression? Right? 1/8 to 1/10 of your compression. So you see at 20 megapascal compression with 1% fibers, with 3% fibers, it's even higher. You see the effect of fibers here. Fibers are bridging all the cracks, and you see how cohesive. These are only 13 mm long fibers, so they bridge the cracks really well. And then that cyclic load testing to show, because it's supposed subject to be fatigue. The connections are fatigue connections, so we need to look at some of these cyclic loads also. And you see here 30 kilonewton loads, very high cyclic load. So we developed a systematic procedure, we have done this, and the bridge tech has been implemented. It's working really nicely, and the department saved a lot of money. Instead of buying a $3,000 per cubic yard, we designed and gave it to them, and then they had a local contractor, a local ready-mix supplier, whom we trained in our labs on how to make this, and he had a small batching plant made just for this job, and it worked out really well. The only thing is the mixing time is much longer, this concrete entire, right from the addition of aggregates all the way to final mix, is about 25 minutes of mixing. 25-30 minutes of mixing with very high admixture quantity. That's something that they had been trained on, and the addition of fiber. So we carefully organized what sample will be, what raw material will be added at what time, and we sequenced all of them, gave them a sequence chart, gave them a test procedure. You can't just stick it under any compression testing machine and test, because the flatness affects the performance extremely well. So you have to really level surfaces, and then you have to do the test on a strain control system so that you can get the entire stress strain curve. So it was implemented, and it's one of the first non-commercial UHPC bridge decks that has been implemented in the US, and at much lower cost. Okay. So some of the ideas that we talked about in the morning: particle packing, implementation of all of that in the actual structure, and the quality control has been extremely good. Okay, quality control in the US is typically not a problem for concretes, but in this case we had to have some additional measures for packing and make sure that, so we had to check the particle size distribution for all the raw materials that were coming in to make sure that they get the predicted strengths that we told them that they'll get. And eventually, at 90 days, they got close to 200 megapascals. We got about 175 in the lab. In the field, they got 200 megapascal because their field mixers are much better than the lab mixers. In the lab, I have my big lab rotatory mixer, but in their field mixer, with all the mass that goes in and the resolution, they had a much better mixing, and fibers distributed really nice. For about 192 megapascals or so, 90 days, which is way more than what was specified. They want 150, we got 150 at a fraction of the cost that they would have spent. Any questions? We did 1 and 3 by volume. 1% and 3% by volume. No, you have to mix and disperse. So it's by mixing. Well, it will be, so at the end of the day, it's not just a speed of mixing. It's a combination of speed and time. Right? It's a combination of speed and time, and speed of the mixer also is a function of, so if you really have a mixer that has speed control. So if I say that normally all the mixers that we have are not speed controlled. Our mixers, we put the material in, you have a medium, high, low, and even if you put in high, for a mix that is so dense like this with little water, it will mix only very slow. So what you want is a mixer that will have power control in the motor, that will give additional power to get you the RPM that you want. So instead of saying rotate at, instead of putting it and saying give me high speed, you're actually saying give me 4200 RPM or give me 3000 RPM. So the motor has to adjust. It's like the accelerator when you do your cruise control, how the car adjusts its speed if you're going up or coming down of the journey. Same mechanism, you need that. If you don't have that, then you need a real commercial mixer that will mix for a much longer period. Because the effect of superplasticizers, even the latest polycarboxylate based superplasticizers, which are supposed to be very quick in dispersing, when you have low amount of water, you basically have to stretch them out by mixing more and more and getting water away from the particles. You get the steric hindrance away, you get the agglomerations away, so you have to get all of that, and that's why it takes long. But good mixing is a key. And that's where a lot of energy is spent on good mixing, and that's where the cost is increased. Yeah. Your fly ash, metagallium, yeah. Good question. So there are ways of doing it. Why would you want to do it? The question is, why would you want to find the contribution of fly ash towards strength? And people have done it in the past. I think it's a waste of time to find the contribution of fly ash towards strength, metakaolin towards strength, silverfuel towards strength. Because strength is an intrinsic property of how well you have packed your microstructure. Strength comes from the physical portion, which is the packing, and the chemical portion, which is the reactivity. there is no way that you can mix the contributions of both. Your chemical part is time dependent, your physical part is really not time dependent, but when the chemical contribution changes, when you have reaction products forming in different parts, your physical packing also changes. So anytime one changes, the other also changes, and there is no one-to-one correlation. So anybody who has told you that fly ash contributes 20% of strength, cement contributes to 90%, silica fume contributes 10%, is just plain lying to you. He probably got it in one result. There's absolutely no way that is true for another set of mixes. Okay? So you can define the reactivity of material. So that's what I would suggest. Find out how much of cement has reacted, how much of fly ash has reacted, how much of silica fume has reacted. That is quantified. And then you say that my fly ash reacted 20%. Just because fly ash reacted 20% does not mean fly ash contributed 20%. Right? There is absolutely no way to break. What people do is, oh, I'll compare this with an OPC where I have 50% fly ash, and based on, I took some strength ratio, and based on that I say my fly ash contributes so much. Nonsense, because in a proper OPC, the physical and chemical reactions are totally different. Right? So don't try to find out how much is the contribution. What you should do if you want to optimize is what every one of us likes. Optimize for the cost. Right? So what you should do is, which one will give me the lowest cost per MPa? If you do that, that is a good way of looking at a number by saying that what is the cost per megapascal. Then you can optimize some. Then you might be able to do much more fly ash than you could have done otherwise. Let the fly ash not react. Why do I bother? If it fills in the space and gives me strength, I'm good.
As a filler material, this will partly packing we can do that. But the contribution of either fly ash or methamphetamine to convert CH into CSH, how much is needed, or how much silicon dioxide is present?
So none of these are exact sciences. People will fool you with. How much of CH gets converted to CSH is that exact. If you measure it at a certain time, you get a certain number. You measure it after 10 more days, you get a different number. You measure it up. See, that's a function of how much your cement actually is hydrated. I talked about this yesterday, right? It's a competition issue. You will have the only way you can kill it is by using silica fume, large amounts of silica fume, because silica fume will immediately react. But even then, anytime your OPC reacts, your calcium hydroxide is produced. And the important thing to note is, anytime calcium hydroxide is produced, fly ash is not eating them up. Silica fume is not eating them up. Anytime calcium hydroxide is produced in solution. Calcium hydroxide precipitates when the saturation level of calcium in the solution rises. When that precipitation happens, then calcium hydroxide has to go back into solution to react with fly ash. Calcium hydroxide cannot react as a crystal, right? So now it has to go back into solution, which means you have to have a calcium deficient system. Your cement paste does not like a calcium deficient system. The moment there is calcium deficiency, one cement grain from somewhere will drop a little bit of calcium in, right? So your fly ash is not reacting with the calcium hydroxide that is produced, contrary to what all of us think. Your fly ash is actually reacting to the balance of deficiency of calcium hydroxide. Now, you throw some sodium hydroxide in the system like you do for Rapley activation. Your calcium hydroxide will say thank you very much, it will sit there, and fly ash also will sit there. Fly ash and calcium hydroxide will not even show that they know each other. They will not do anything because sodium is now more powerful than calcium as a cation, and sodium will say, I'll do my job, you guys keep going. Right? So this, and if you have a cement with a higher alkali content, that's exactly how it's going to happen. So if you have a 1 or 1.2% sodium oxide in your cement and you're expecting your fly ash to do your conversion, you will not get the conversion that you need. Right? So there's a lot of complicated stuff. So that's why go with performance. Go with what performance I need, and it's good to understand and know and control all of those, but you can't control concrete like you control your children. Okay? So I had a professor who once told me, we had a fight about this when I was doing my master's. I wouldn't enter into a fight now, but at that time you're so excited about this stuff. Right? So this guy came to my master's defense. I was explaining some mechanism, and he told me that concrete behaves the way it wants to behave and not the way you want it to behave. Fair enough, right? And after some time, he started to explain a mechanism which was kind of wrong. So I gave him back. I told him, you just told concrete behaves the way it wants to behave, and why are you trying to explain? And he didn't talk to me for about a year or so, until both of us were consultants in the same project that we had done. But the point is that there's so many mechanisms. To isolate any of those, this is like human body, confounding mechanisms, right? So, simple example. If your thyroid stops working, and if you have hypothyroidism, your body starts producing more cholesterol. They are totally unrelated things. But the doctors will tell you, if you have hypothyroidism, you will have more cholesterol. Totally unrelated. But it's in this one big mass, there are a lot of reactions, a lot of things that are going on. And that's why, are you healthy? Are you well? Can you run? Can you eat? Good enough. Don't go too much into exploring what it is. It's good to, from a starting point of designing to know what it is. Perfect.